Okay, so I want to discuss a little bit, and I won't be able to go through some of the detailed derivations of how the cosmological collider of physics works. But what I do want to do in the time I have is tell you a few kind of standard and concrete things, which we can easily do in the allotted time, which will let you understand all of the main aspects of the story. And in fact, in order to do it, I want to back up, and before getting to cosmological collider physics, I want to remind you about how we can probe for the existence of resonances in ordinary collider physics, okay, ordinary standard particle physics. And so here, in order to make life a little bit simpler, let's imagine that we're scattering scalars. Okay, in the real world, we have gauge fields and fermions and other things. Imagine we're scattering Higgses or something like that. Okay, so we have a collider that's scattering scalars, and people do experiments, and they discover that the cross sections have these spikes at certain locations, right? So they scatter two scalars in, two scalars go out. So they're doing 2-to-2 scattering for scalars, and they see spikes, they see resonances. How can they tell what's going on? How can they tell what the masses and the spins of the particles that you are producing are? And do they need smart information from a theory? Do they need to have a Lagrangian? Let's say, and this is literally what happened in the 60s, right? People went, they found higher and higher spin states. Of course, they weren't particularly narrow. So I'm going to imagine that I'm in an approximation where there's even a weak coupling, so all the states are narrow. Okay? Well, let's say you sit there and there happens to be a spin 7 particle in nature. Okay, and this massive spin 7 particle, and the scalar couples to it. Okay, how do you know what the amplitude is supposed to look like? So in fact, what I want to do in this first part of the lecture is tell you what the general structure of any 2-to-2 scattering amplitude for scalars can look like. Okay, with the assumption that there's a weak coupling. All right, and so to begin with, what's the very, very simplest thing that we could imagine? Let's say the scalars are identical for the sake of this argument. So what could the 2-to-2 scattering amplitude be? They have some mass m. Okay, they don't even have to be massless. Well, the amplitude could be a constant. Okay, so the very simplest thing would be a constant. It could be, now we could have other things. We could have some function of s. And if it's going to be invariant, permutation invariant in all the 4 labels, I can have some other constant times s plus t plus u plus some other constant s squared plus t squared plus u squared plus ... Okay? In fact, in a little bit of detail, this first thing, s plus t plus u, is actually equal to 4m squared, right? So this is actually a constant anyway. So this is reabsorbed into the constant piece. And so then I have a polynomial dependence to begin with. Okay, so if you want to organize your thinking about what the amplitude can look like in terms of simplicity of the function, the very simplest possible thing that it could be is analytic. Right? It's just a polynomial when you expand around low energies. Okay, near st and u is 0, or near m squared, little m squared. It could just be something totally analytic. Right? So that's the very first approximation that we can make, is that it's analytic around, I'll call it the origin, even though I mean m squared. If it was massless, it would be the origin around the origin. Okay, so that's the very simplest possible analytic structure you could imagine for an amplitude. Okay, and that's what happens again in real life. If we have, as we said yesterday, we have e plus e minus, the mu plus mu minus, then at very, very low energies, if we ignore the photon, well, there's a piece that comes from the photon. We can talk about that as well. That piece is not analytic, right? But if we ignored, if we just look at the weak interactions, better example, right? Neutrino electron scattering, that's an amplitude that's totally analytic around the origin. Okay. Now, because it's analytic around the origin, it's growing as a polynomial, right? So anything which is analytic around the origin cannot be the amplitude forever. Okay, there's dimensionful coefficients out there, and at some point these amplitudes are going to become larger than 1. Okay? So that can't be the whole story for what the amplitude looks like. So what's the next simplest thing that could happen after saying that it's just dead analytic as a function of these variables? It can have poles, right? And if we have a theory with a weak coupling, that's the leading kind of analytic behavior it can have. It has poles at tree level, if you imagine you had a Lagrangian. And then at loop level, you get more complicated functions. At loop level, you get functions that have branch cuts, because the imaginary parts, or the discontinuities across the branch cuts, have got to be matched by the optical theorem by tree level cross sections, for example. Okay? So the next most complicated thing is that you have poles. But now there's a very important constraint. The very important constraint is that if you have a pole as s goes in the neighborhood of some capital M squared, right? That means that the amplitude in that region looks like 1 over s minus m squared plus I epsilon. Okay? And if you sit right around s equals m squared, okay, this amplitude is real everywhere, but right in the neighborhood of s equals m squared, it acquires an imaginary part. And this imaginary part, you know, as you know very well, this imaginary part is delta of s minus m squared. Okay? So that's good. That means that it acquiring a pole has a physical interpretation. It's a resonance, and it means that I've produced a particle. All right? Because I've produced a particle, the residue on the pole, okay, so this is just what the pole looks like, but what does the full amplitude look like? The full amplitude has got to look like, and this is something that Cliff will exploit a lot for massless particles, but here we're going to do it for the case of scalars and a massive particle. Near the residue, as s goes to m squared, the amplitude has got to go like 1 over s minus m squared, but then you have to be able to interpret the numerator as the amplitude for these scalars producing some intermediate resonance, and the resonance going and decaying on the other side. So there's a 1, a 2, and a 3, and a 4. And here I have to have some particle that has mass m, perhaps it has some spin s, and I have to sum over all the possible polarizations that this guy can have. Okay? And I put a lambda and a minus lambda simply because in writing down these amplitudes, we're imagining that all the particles are incoming. Okay, so if it has positive, if it has spin in one direction, it has opposite spin in the other direction, if everything is incoming. All right, so this is the big constraint, that the residue has got to be interpreted as the production and decay of some particle of some spin, which we don't know. Okay? Or maybe a collection of particles with some spin. I'll call the spin little s. Okay? Curly s. Okay, so now the question reduces to a more primitive one that we, logically speaking, really should have started with, which is, can we say anything about the 3-particle amplitude, the on-shell 3-particle amplitude, for 2 scalars and any old particle of any spin? All right? And as you saw in Cliff's lectures yesterday for massless particles, this is an object which is actually completely determined by symmetries, up to an overall constant. So let's see why. Right? So what could this amplitude depend on? So let's say I have scalar particle 1, scalar particle 2, or momentum 1, momentum 2, and I have this guy. And this guy is going to be a spin s particle. So first of all, how do I describe the state of a massive spin s particle? Let's back up. How do I describe the states of a massive spin 1 particle? So we talked about that yesterday. I have to give you a polarization vector, epsilon mu of p. Okay? But that's something which has 4 degrees of freedom, the massive spin 1 particle has 3 degrees of freedom, and so I have to impose this constraint that p mu epsilon mu equals 0, which is obvious in the rest frame. It just says that all of the polarization components are spatial. Okay? So how do I describe a massless, a massive spin 2 particle? You see, here, yesterday I railed against polarization vectors, because polarization vectors are redundant things for massless particles. At least for those of you who are in the discussion. They're not invariant things. They're redundant things. But for massive particles, they're fine. Okay? I put this constraint, everything is totally fine. There's no reason not to use them. Right? Okay, how do I describe a massive spin 2 particle? Well, it's an epsilon mu nu of p. It has to satisfy that p mu dotted into it is equal to 0 for any components. All right? But it also satisfies one more constraint, which is that, so what if we go to the rest frame, what would this look like? Okay, so if we go to the rest frame, if I go to the rest frame, this says that the only non-zero components would be epsilon ij. Okay, if I have p mu is m0, then this would say that the epsilons only are non-zero in the spatial components. Right? That's good. That means that these polarization vectors transform like a 2-index symmetric tensor under SO3. SO3 is a little group, right? Just standard rotations is a little group. But if I want to talk about a spin 2 particle, what is a spin 2 particle? If I want to use tensors to describe a spin 2 particle is a symmetric tensor, but it's also traceless. It's a traceless symmetric tensor. Okay? If I just say I have a symmetric tensor, there's both a spin 0 and a spin 2 component in it. Okay? So I have to say that in this frame, epsilon had better be traceless. Right? So I want to say that epsilon ii is equal to 0. And while the Lorentz invariant way of saying that is that I impose this condition and that epsilon is traceless. Okay? So that's how we describe just a polarization vector. A polarization vector for a spin s particle in general now. So if I have a spin s particle, its polarization vector is epsilon mu1 through mu s of p. It satisfies that p, any mu1, epsilon mu1, everything else is equal to 0, and it's traceless in any pair of indices. Okay, so that's what describes the polarization vector for a massive spin s particle. Okay. Now we know what the polarization vectors look like. Let's go and let's try to write down an amplitude, that 3-particle amplitude. What could it possibly be? Let's start with a spin 1 particle, just for fun. Let's do a massive spin 1 particle. Okay, and if we have a massive spin 1 particle, then if I have these two scalars, 1 and 2, okay, so there's some, I have to contract a polarization vector. Okay, so what could it be? I have epsilon mu that depends on this momentum p3, and it can be all I have are momenta, right? So it can be a p1 mu plus b p2 mu plus c p3 mu. That's the most general thing it can be, right? Now, p3 dot epsilon 3 is equal to 0. Okay? So this is the same as epsilon mu p3 a p1 mu plus b p2 mu. But also p1 plus p2 is equal to minus p3. Okay? So this is really the same as, so that means that the piece here, I can break this up into something p1 plus p2, it's something p1 minus p2. The something p1 plus p2 also vanishes. So all it can be is epsilon mu, some constant, g epsilon mu times p1 minus p2 mu. Right? And again, note we didn't have to write down a Lagrangian with derivatives and worry about, that's just all it can be. Now notice just a small amusement right here. We discover right away, for instance, that I cannot have a coupling of a massive vector to a single real scalar, right? Because that would be antisymmetric in switching 1 and 2. So it would violate both symmetry. So the only thing I can have is a massive vector coupled to 2 different scalars, okay? Or a charge scalar, for example, which is 2 neutral components. Right? So all these little things, which you know, are just obvious from staring at the amplitude. Okay, very good. So that's the amplitude for massive spin 1. So what is the 3-particle amplitude for any old spin? For spin s, well, it's just the obvious generalization. It's just some constant epsilon mu1 through mu s, and then it's just p1 minus p2 mu1 up to p1 minus p2 mu s. Right? Okay. So this 3-particle amplitude is nailed by Poincare symmetry, right? We used translational invariance, momentum conservation, as well as Lorentz invariance, and up to a constant, it's nailed by Poincare. Yes?
For spin even particle, then identical scalar can come to spin even particle.
Yes, identical scalars can couple to spin 2s, 4, 0, 2, 4, and so on, okay? But not to odd. Okay, now let me just take a small digression, because this is for scalars on the outside. What you saw from Cliff's lecture yesterday is that for massless particles, for any helicities, they're completely nailed by symmetries. And it's a little exercise, a little homework exercise that you can do, and I'll do a small part of right now, which is, let's say that you want to keep this guy to be massive, but you want these guys on the outside to be massless particles with spin. Okay? And now ask the question again. How much can we say about the structure of this amplitude? See now, yes?
But now the scalars are massive.
The scalars can be massive. Massive or massless, it doesn't make much difference. Okay? But let's just pause for a second and imagine that these guys here were massless particles. Massless spin 1 particles, massless spin 2, whatever. Okay? Then it's really convenient to use polarization vectors for the massive particle. Nothing wrong with that. But to use spinor helicity formalism for the massless particles. Right? So you do the very best thing you can for everyone. And let's just do a little example just to show you how fun this is. And the little exercise for you to do is to figure out what all the structures are that you can write down when you couple to a massless spin 1 particle, a massless spin 2 particle. It will no longer be unique. You'll have a number of structures, but you can figure out what the structures are. But let's just do a little exercise to see what this looks like for trying to couple a massive spin 1 particle to 2 massless spin 1 particles. Okay, so this is massive spin 1, and this is massless spin 1. Okay, so it has various helicities, so we could try various combinations. For example, we could try the combination where that's minus minus. Let's try that amplitude first. Okay? So what do we have to do? We have this polarization vector here that has an alpha and an alpha dot index. Okay? And we have to contract it. Okay, we can contract it with P3. That vanishes. So we can contract it with something made out of the spinor helicity variables for particles 1 and 2. Okay? In some combinations. So let's actually try a simpler exercise first. Let's say, just to write something down immediately, let's say I want something that has helicity plus a half and minus a half. So these are fermions for a second. Okay? Okay, well, how would I do it? what I need to do from Cliff's lecture yesterday is write down something that has weight 1 in the lambda for particle 1 and has weight 1 in the lambda tilde for particle 2. Okay? Because that's what we get from the little group. And well, that's easy peasy. It's just lambda 1 alpha, lambda 2 tilde 2 alpha dot. Okay? Sometimes these things are written in a way that's as lambda 1 epsilon lambda tilde 2. Okay? Beautiful. So that is a 3-particle amplitude for a massive spin 1 particle to couple to 2 massless fermions of helicity +1 and -1. Okay? So let's return to the problem at hand. Let's say we try to write down the coupling for 2 massless spin 1 particles. And let's start with this one again. Okay? Well, what can I do? I can couple this guy to, again, I can take this epsilon and I can dot it into, for example, P1, which would be the same as P1 minus P2. So that's exactly what we talked about last time. So I could do that, epsilon dot P1 minus P2. That doesn't have any little group weights at all. And now, out of what's left, which are just the lambda 1 and lambda 2, I have to build something that has weight 1 in lambda, weight 2 in lambda, and weight 2 in lambda tilde. And you see, there's no way I can do it. Because I could write down, for example, if I wrote down epsilon dot P1 minus P2, I would write down 1, 2 to the A, angle bracket 1, 2 to the B. And there's just no way, right? There's the same numbers of 1s and 2s. I can't make an asymmetry between them. I can't make it have a total of -1 for one and +1 for the other. Okay? Okay. Okay, so what else can I do? I can do like lambda 1, epsilon, lambda tilde 2, just like I did there. And again, I could try to multiply by 1, 2s and angle bracket and square bracket 1, 2s, and there's nothing I can do which gives me the right weights in 1 and 2. Okay, well, you say, okay, maybe that helicity doesn't happen. Now we try this one. Okay. Now that one is more promising. Okay, because here I can write down, for example, I can write down epsilon dot P1 minus P2, right? And then I can just write down angle bracket 1, 2 squared. Great, that has the right weights. Everything is fine with that. But it has a small problem. It's antisymmetric when you exchange 1 and 2, so it violates both symmetry. Okay, so you can't have that. And then if you go back and you try to do the same thing, anyway, the last possibility is when you contract it like this, and cousins, and again, you can't do it with the weights. So this is interesting. It's impossible to write down a consistent 3-particle amplitude for a massive spin 1 particle and 2 massless spin 1 particles. Do you know this fact? This is called Young's theorem. Okay? So this is why a massive spin 1 particle can't decay to 2 massless spin 1 particles. Okay? All right. And we actually see the assumptions that go into the theorem by trying to write down the amplitude. We assume both symmetry. If we violate both symmetry, we could do it. And we assume Lorentz invariance. Why is Lorentz invariance important? Because if we didn't have Lorentz invariance, let's say we go back to this example, and we had something that looked great. See, this would be great if it made sense to write this down. If I could contract a lambda 1 and a lambda tilde 2, everything would be perfect, right? Then I'd have 2 lambda 1s, 2 lambda tilde 2s, and everything would be perfect. So it is possible to write something down if I contract the lambda tilde 2s with the lambda 1s. It's not Lorentz invariant, but it's perfectly rotationally invariant. Okay? Okay? Because the rotational part of the Lorentz group is just something which does not distinguish between the alpha and the alpha dot indices. So, that's what you all know about Young's theorem. It's always a little mysterious that everything is fine with angular momentum conservation and, but it's really Lorentz invariance in both symmetry, which is the heart of it. And so we can discover it in this extremely trivial way, just trying to write down the answer. Okay? Yes.
If I try to add angular momentum, 1 plus 1 equals 1, the angular momentum of the two ones is antisymmetric, and trouble from those statistics again is even easier.
No, in this case, everything is fine. Everything is in this case, everything just for rotational invariance, everything is actually okay. So you really need both symmetry and Lorentz invariance in order to have have the statement. Sorry. Where have I used the thing coming out with this thing? Nowhere. In fact, the amplitude for the in here, I'm not using that it's here. I'm not using that it's here. It doesn't matter that it's massive or massless. The reason for the vanishing of the but when the particle is massless, it is possible to have this. It is possible to have a 3-particle amplitude. When this particle is, it's not possible to have a 3-particle amplitude when all the particles are different. Okay, but it is possible to yeah, what's going on is that so the massless amplitude, the massless amplitude for real momentum vanishes for other reasons. Okay, it vanishes just because of the kinematics of being impossible to have a massless particle split into two others. But I think this expression, well, this expression vanishes anyway. Okay, and it's telling you, as you take the massless limit, not only do the transverse polarizations not have any ability to decay, but nor do the longitudinal ones. That's what we learned from this extra argument. Okay. Anyway, so I leave it as an exercise to figure out how you can do the analog of this exercise for any, let's say for massless spin 1 particle, for how it can couple to any spin. And you can figure out what the allowed structures are. Okay, so let's return to the main line of investigation. Now that we know, let's go back to the case of scalars. Now that we know what the 3-particle amplitude is, we know what the residue has got to look like, right? As s goes to some m squared, the residue has got to equal the sum over the polarizations, right, of that. And this is the sum over the polarizations. There's some g squared. And it's a sum over the polarizations of epsilon of p1 minus p2 mu 1, p1 minus p2 mu s. Then there's p3 minus p4 nu 1, p3 minus p4 nu s. And then we have the sum over the polarizations of epsilon lambda mu 1 through mu s, epsilon minus lambda nu 1 through nu s. Okay. Now, what is this tensor? Okay. When we sum over the polarizations, all we can get are eta etas, eta etas all over the place. We can contract eta etas all over the place. So what we get is a big tensor made out of etas that's fully symmetric in all the mu indices, fully symmetric in all the nu indices, and is traceless in all the mu indices and all the nu indices together. So this is a little group theory problem. Okay, so how do you figure out what those tensors look like? Right? Now, we're going to figure out the answer to this question, but just to skip ahead, this is supposed to be familiar to you, even though we do it in old quantum mechanics courses and it doesn't tend to stick in your head. What we're doing is just the famous partial wave expansion. Okay? We know what the answer is supposed to be. The answer is supposed to be that that we have to be able to interpret this residue as a sum over partial waves, and in the numerator we're going to get Legendre polynomials. Okay? And they're in 3 dimensions are called Legendre polynomials. In general, you can call them in d spatial dimensions, d-dimensional Legendre polynomials. They're called Gegenbauer polynomials. But what we're going to do is now derive that from this particle physics perspective, summing over polarizations. And as a bonus, we're going to understand everything there is to know about Gegenbauer polynomials, so you don't have to look it up in a book. Okay, so you can remember where it comes from and actually derive it every time you forget. Okay? Huh? These are the polarization vectors. Okay? One for lambda and one for negative lambda. Okay? All right. So the first thing to do is to conveniently do this calculation, again, in the rest frame of the intermediate particle. Okay? In the rest frame of the intermediate particle, the only non-zero component of the epsilons are the spatial components, right? And P1 minus P2 is just the spatial P1 minus P2. P3 minus P4 is the spatial P3 minus P4. And so in the center of mass frame, right, in the rest frame of this of the intermediate particle, P1 minus P2 is the direction of the beam. P3 minus P4 is the direction that the particles come out at. Okay. So when we go to the rest frame now, we again have just the sum over all the possible polarizations of something that looks like epsilon I1 through IS, epsilon J1 through JS. And then I have, let me just write it in general, xi1 to xis, yj1 through yjs, and x happens to be p1 minus p2 vector, y happens to be p3 minus p4 vector. Okay? And we know that this sum is going to give us symmetric and traceless big tensor in everybody, right? But in the end, since it's all a bunch of delta deltas, right, this is just going to be some function of x squared, y squared, and x dot y. Okay? So we'd like to know what function of x squared, y squared, and x dot y is it. In fact, this is just guaranteed to be, you know, x to the power of some s, x to the power of s. The distance is y to the power of s times some function of cosine theta, right? Some function of the angle x dot y over x y, right? I mean, in detail, there are pieces that look like x squared, x dot y to various powers, all right? And so it's really just x to the s, y to the s, some function of x dot y, or some function of the angle. Okay, now how can we figure out what this guy is? You can start off and just do it by hand. You can do it by hand for a few examples. You write them down, you subtract the traces, you keep going. But it's a little painful to do it all the time by hand. Okay? So there's a very nice picture for what it is where you don't have to do any calculations. And it also makes it very clear why it's related to the spherical harmonic expansion. Okay? And the reason is that if I think of this function, if I think of this as a function of x and y, so this is some of g of x and y, then the traceless condition, it's a traceless condition which is the hard part, right? The fact that it's symmetric is what tells us it's just functions of x dot y and everything else. It's the tracelessness which is the hard part, okay? But the traceless condition is completely equivalent to the following statement about the function g. Okay? Tracelessness just tells me if I take out any two x's and I contract the two indices, I get 0. Right? So tracelessness is the statement that if I take d by dxi, d by dxi1, d by dxi2, delta I2, I1, I2 of g, it's equal to 0. Right? Because that's how I take out two x's. I differentiate with respect to one x, I differentiate with respect to another x, and then I contract them. Well, that just tells us that g solves the Laplace equation in x. Okay? And therefore, there's a beautiful generating function for all of these things, for all spin s, that I can get just by writing down any old solution of the Laplace equation. Okay? So let me write down any old solution of the Laplace equation in d dimensions. Okay? Any old solution is, I can say that I put some charge at y, and I look at the potential generated by the charge at y. Okay? So that potential would be 1 over x minus y to the power of d minus 1 if I'm in d spatial dimensions. Okay? So this is where the charge is, and here is where I'm doing where I'm measuring the source. So this, of course, obviously satisfies that the Laplacian of v is 0 away from y. Right? And so let me do a Taylor expansion in x around some origin. If I Taylor expand in x, I'm going to get 1 over y to some power plus an expansion in powers of x. Each one of them is going to be a term with some number of x's and y's when I expand it out. And therefore, the expansion of this, every term, is going to precisely give me the answer to what that polarization sum looks like. Okay? So that's the connection between the particle physicist's way of thinking about this problem as summing over the polarizations of the intermediate states, and the old-fashioned quantum mechanics way of doing it as just a partial wave expansion, given what you know about the rotational symmetry of the problem. Okay. So that's the answer that we're looking for. In fact, if we write down, over d minus 2, if I'm in d spatial dimensions. And this is the definition. 1 over x minus y to the d minus 2 is equal to, we can pull out a 1 over y to the d minus 2 times the sum of x, these magnitudes x over y to the s, times what you can call ps, maybe I'll call it g, because that's sometimes what it's called, the g of s, and it depends on the number of spatial dimensions, of cosine theta. Okay? That's just a definition of what these guys are. Okay? So that's a generating function. When I just do this, you shove it in the computer. In other words, this is 1 over x squared plus y squared minus 2x dot y to the d minus 2 is equal to this. And in fact, if I want to do it a little bit more efficiently, I can always normalize, just for the purpose of this discussion, I can normalize the magnitudes of y to 1, x to r. So this is really the statement 1 over 1 plus r squared minus 2r cosine theta. That's the angle between x and y, to the d minus 2 over 2 is equal to the sum of r to the s, g s of d of cosine theta. Okay, so that's the definition. And that function of cosine theta is what can appear in the numerator of our residues. So these are called Gegenbauer polynomials. And they're just the analog of spherical harmonics in any number of spatial dimensions. Okay, any questions about this? This is extremely basic. Okay, it's as I said, in principle we learn it when we learn quantum mechanics, but it's nice to see explicitly the connection between the partial wave expansion from quantum mechanics and just the most obvious summing over polarizations that we do in particle physics. Okay, so let me just write down some of the Gegenbauer polynomials to see what they look like. It won't be so important right now, but it'll be important for my lecture in the afternoon. I'll just write down what they look like for spin 0, 1, and 2. So for spin 0, s equals 0, in any number of dimensions, g, 0, and d is equal to 1. For spin 1, g, 1, and d is equal to cosine theta of cos theta. Cos theta for spin equals 2, g2 and d of cosine theta is cos squared theta minus d cos squared theta minus 1. Okay? So that's where the dependence on the dependence on the spatial dimension comes in. Okay? And so on. All right, so let's now summarize. So we know that near a pole as s goes to m squared, near a pole as s goes to m squared, the amplitude has got to look like 1 over s minus m squared times what? Times a sum over a bunch of particles, sum over species, some g squared for that interaction. So sum over species, I don't know, I, g squared I, and the numerator's got to be a Gegenbauer polynomial, if I'm in d spatial dimensions, g, s, and d of cosine theta. Okay, so this is coupling also for the particle of some spin. The crucial thing is that this g squared is positive. Okay? That's what tells you that the amplitude, when it develops a pole, can be consistently interpreted as producing a particle. The residue has got to be expressible as a positive sum of Gegenbauer polynomials as a function of the angle. So the very last thing to do is to just, if you want to just translate this back into in language of ST and U, and for that there's just a little bit of kinematics that I won't do for you. It's 2 lines. If you've never done it before, you should do it in the time I finish writing, erasing the board. Okay. What is the relationship between S, T, and the scattering angle? And that angle cos theta. Okay. And the relation is that T is equal to S halves minus 2m squared. This is the particle, mass of the particle that you're scattering, times cosine theta minus 1. Or therefore, cos theta is equal to 1 plus 2t over s minus 4m squared. Okay?
So can you say again, what if this is negative?
If it's negative, that coupling is a positive number, so its square is positive. If it's negative, that means that you've written down an amplitude that does not deserve to be called an amplitude. It has negative probabilities. Okay? All right, so now let's really fully summarize this story. As s goes to m squared, the amplitude has got to look like 1 over s minus m squared times some sum with positive coefficients. I'll be schematic here, g squared. But these Gegenbauer polynomials, g, s, in d dimensions, of cosine theta, which is 1 plus 2t over s minus, and s is around m squared now. So I can put, instead of s there, I can put capital M squared minus 4m squared. Okay? All right, so that's what the amplitude has got to look like in the neighborhood of a resonance. And that's why experimentalists don't need theorists to interpret what happens near resonances. Okay? Because theorists are supposed to do more than keep track of symmetries. Anybody can do that. Theorists are supposed to understand something about dynamics. This has nothing to do with dynamics. Okay, it's fully 100% specified by Poincare symmetry. Okay? So, now that's in the S channel. So in the T channel, it would look like 1 t minus m squared, something similar. So let me just write it plus t plus u. Okay? And now why am I writing amplitude equals? This is just what it looks like at the pole, near the pole, right? Is not what it looks like everywhere. But let's say I write the amplitude is, there's the amplitude, and let me just write these functions down. This is on the pole, this on the pole in t, that's on the pole in u. So now the difference between the left-hand side and the right-hand side doesn't have any poles anywhere. Okay? So what can it be? We go back to the first things we could have. They could just be polynomials. Okay? So we can have plus polynomials in S, T, and U. Okay? And so we've determined on entirely general grounds what the most general possible four-particle amplitude can look like in a theory where you've seen a finite number of particles. Okay? You see a finite number of particles, and once you see them, the structure of the four-particle amplitude is completely nailed. Right? It is completely nailed to be these Gegenbaurology over on the poles. And then once you take care of that, everything else can just be a polynomial. All right? Okay, any questions about this?
So what's
Yes?
the rule out the possibility that the product of STU channels instead of being a sum of STU channels?
Oh, well, we can't. Well, we'll see some of that in our derivation of string theory in the next lecture, in our quasi-derivation of string theory in the next lecture. But you can't. So you say, why couldn't I have? So let me. But this is a very important point. Okay, it's very important that the residue in the S channel is not only a positive sum. That's really, really important, but it's just a polynomial. Period. Okay, if it's not a polynomial. So I can't have, so if someone says, here's the amplitude, it's 1 over s times t minus 1, you're screwed completely. Okay, 1 over s minus m squared, let's say, times t minus 1. Then this means there's an infinite number of particles at mass m squared. Okay, because 1 over t minus 1, you can expand in powers of Gegenbauer polynomials, and it's an infinite expansion. Okay, so we're assuming we have a finite number of particles. So it has to be a polynomial even to begin with. Okay, never mind that the polynomial is got to be positively expandable in terms of the Gegenbauer basis. Okay. Any other questions about this? All right. Yeah, but we don't see the width in this approximation. So this is the approximation where it's a perfect pole, and then if we go to one loop, we would see the width. The width has to do with a correction to this picture of the amplitude, which doesn't just have poles anymore. Okay. So we're just talking about weak coupling, some first approximation to the amplitude. Maybe I'll just make one other comment. Here we are talking about a scalars coupled to a massive spin-s particle. What would it look like if we're coupling to a massless spin-s particle? Okay. What do you think is going to happen? Now, this is something you don't need to do in this way because Cliff is explaining how to do it more beautifully, at least in 4 dimensions. But let's say we can just keep going in this way of doing things, and we get the answer in any number of dimensions to boot. Okay. So, what is the what will we get when we sum over these polarizations? What do you think we're going to get?
0.
No, we're not going to get 0. No. No, I mean let's forget. Let's not worry whether they're identical or not on the outside. Okay, so I just want to do, when we do this sum over the intermediate polarizations, what do you think we're going to get? When it was massive particles, we got the Gegenbauer polynomials in d spatial dimensions. What do you think we'll get if they're massless? What would you guess? The little group is one lower dimensional. So mass of particles, the little group is SOD. For massless particles, it's SOD minus 1. That's the only difference. Okay? So it's exactly the same, except that for massless particles, exchange, we just replace GS of D with GS of D minus 1. That's it. Now this is a little bit cool because we'll notice if we're exchanging spin 0 particles, the limit is smooth. Because the Gegenbauer polynomial is the same in any number of dimensions. If we're exchanging spin 1 particles, the limit is also smooth. But if we're exchanging spin 2 particles, spin 2 is the first time that the Gegenbauer polynomial depends on D, and the limit is not smooth. Okay? So when you have a massive spin 2 particle, and you send the mass to 0, the amplitude does not smoothly go over to a massless graviton exchange. If you know anything about the horrible subject of massive gravity, then you know this is one of the most famous ancient things that was discovered. It's called the Van Dam-Veltman-Zakharov discontinuity, the VDVZ discontinuity. And in conventional ways of doing it, there's sort of complicated things, like the propagator and this and limits and that. But, well, here we just get it immediately. Okay? It's just that starting at spin 2, the Gegenbauer polynomial has a dimension dependence, and so there's just a drop. And you can even just compute, you can compute what it is. Okay. All right. Good. So now that's the story for ordinary collider physics. And what I'm just stressing again is that what the signals are for the presence of new particles is completely unambiguous. Now, what is the thing that is not unambiguous is all these polynomial pieces, right? These polynomial pieces are not fixed by symmetries, even though we know what their structure is. They're just polynomials. But the coefficients aren't fixed by symmetries. Well, of course, neither of the other ones. But how many of them are the structure of them? There's lots and lots of unknowns in the polynomial pieces. Okay? But what happens on the resonances, what happens on the poles, is nailed up to the overall constants. And for the umpteenth time, you have a spike. And there's an angular dependence on the spike, which is the Lejeune polynomial or Gegenbauer polynomial that tells you the spin of the particle. So, again, if we're sitting at very low energies, we don't know there's W's there. All we know is that the amplitude is some analytic function of ST and U. We have no idea what all the coefficients are, or everything like that. But if we go produce the W, we know ahead of time what it has to look like on the pole. Okay? All right, so this is all super familiar, but now we're going to port it to the cosmological example. Okay. All right. So let's now switch to the cosmological collider. And here, I'm going to have to be a little more schematic, but given everything that we've seen, you'll believe everything about the structure of the final answer. Okay, and that's what really matters. So to begin with, let me draw pictures like this. When we imagine that we're talking about inflation or cosmology, and presumably we'll see many pictures like this from Matthias later. We can imagine that there is a time, a conformal time. Okay, we can write the metric as some a squared of eta, and we pull out the overall minus d eta squared plus dx squared. Okay, and if we're doing an inflationary calculation, a of eta during inflation goes roughly like 1 over eta. Okay, and so we have this sort of future. Very late time spatial slice. And it's this very late time spatial slice, of course, inflation ends. And so all the stuff that was produced by inflation and goes way outside the horizon is imprinted on this very, very late time spatial slice. And we can calculate all possible correlations that are generated by inflation on this late spatial slice. And that's the things that we observe in the sky as density fluctuations. Okay? So in this picture, you can think of the conventional two-point function as coming from a Feynman diagram that looks something like that. Okay, just the I'm measuring something here, delta rho over rho here, delta rho over rho there. The proxy for that is the inflaton here, the inflaton there. Okay, and I'm measuring the 2-point function of the inflaton. Okay, so this is really measuring phi of x, phi of y, or in position space, in momentum space, some delta cubed k1 plus k2, just some times the 2-point function, and the 2-point function, as we said, is roughly 10 to the minus 5 squared over k cubed. Right? So that's what's coming from the 2-point function. And it's basically scale invariant. Just by units, this is dimensionless. And when I go there, this thing should have units of 1 over k cubed. OK, let me just call this delta rho over rho. Okay. OK, now, and as we said yesterday, that is essentially entirely determined by symmetries, and we're going to even assume that we have the approximate de Sitter invariance. Although here it just depends on scale invariance. So a big program of cosmology in the coming years is going to be to measure the 3-point function, the 4-point function, and higher, right? And so we might want to know what is delta rho over rho at x1. In general, delta rho over rho at xn. And this is going to be some, back in Fourier space, will be a delta function, sum of k1 through kn, times some function that depends on k1 and kn. And the way cosmologists will typically draw this is they say, for example, if you're drawing a 4-point function, they will draw a square, right? A square with the momenta, the side lengths being the momenta, and they all add up to 0. OK. So that's the data, right? What do these non-Gaussianities depend on? You have to give a bunch of k's that add up to 0. Right? You give a bunch of k's that add up to 0. There's a number associated with that from measurements in the sky. We can do 3-point functions. Okay? But let's look at this 4-point function for a second. Now, that's the way cosmologists would draw these 4 vectors. How would a particle physicist draw these 4 vectors? See, we're very used to 4 vectors that add up to 0. We call it a scattering process. Right? So we'd say, for example, k1, k2, negative k3, negative k4. That's exactly the same thing. The data that labels a cosmological correlator is the same as the data that labels a scattering amplitude. Okay? It's a bunch of momenta that add up to 0. In fact, not quite, because the scattering amplitude imposes one further constraint that we don't have in cosmology, which is that the energy is also conserved. Right? So there's an energy associated with the particles. So we say magnitude root k1 squared plus m1 squared plus root k2 squared plus m2 squared is equal to root k3 squared plus m, and so on. Right? We don't have the analog of that in cosmology. There aren't actually particles here. So this is just an analogy saying these cosmological correlators depend on one extra variable, one variable on top of the variables that ordinary amplitudes depend on, because we don't have the analog of momentum conservation. OK. OK, so let's go and imagine what the non-Gaussianities can actually look like. Okay. So I want to take 2 examples. Let's say that we have some. So we have inflation. We have a scalar. It has a potential, a small potential. But let's say we have some self-interaction between the scalars, right? Let's say we have something like d phi to the 4th, okay, over some scale, right? So there's a very simple example of some self-interactions that we can have between the inflatons, right? So that's coming from a contact operator. Some very heavy particle, something we integrated out, we have these interactions between the inflatons. how do these interactions give rise to non-Gaussianities? Well, the first thing you can do is imagine taking phi, and first you want to expand it around the inflationary background, plus delta phi. It's these delta phi fluctuations which are what are giving rise to delta rho over rho. So just schematically, from here we see that this is already going to give us, even though it's a d phi to the fourth, we're going to get things that are like d delta phi cubed times something like a derivative that acts on the inflaton. Again, the inflaton is rolling, so we'll get something that looks like a phi inflaton dot. Right? So despite the fact that we start with quartic interactions, we get a 3-point interaction between the inflatons. It's a little suppressed because the inflaton is rolling slowly. Okay, so phi dot is of order the slow roll parameter in inflation, epsilon. Again, I'm being quite schematic, right? But we see that from this underlying contact interaction, we can get a nice 3-point interaction between the inflatons. And in fact, the 3-point interactions are secretly 4-point interactions of the underlying approximate de Sitter space, where one of the legs is put on the background. Okay, so I'll just remind myself of that by drawing it like this. And then one of them, I just imagine, is a leg that was put on the background. Okay? So that's the sort of that is a sort of diagram that would contribute to this 3-point function. Okay, now without saying anything more, even telling you how to explicitly do these computations, that will be a subject of another few lectures, although it's extremely easy. What can this 3-point function possibly look like? Okay, and what it can look like is the following. Let me write down the answer. It looks like 1 over magnitude of k1 plus magnitude of k2 plus magnitude k3. So there's an overall epsilon. Okay. But it looks like some power of 1 over magnitude k1 plus magnitude k2 plus magnitude k3 to some power. And the power will depend on what the derivatives are, if I had them, not had them, whatever they are. And upstairs, it'll be a polynomial in the k's. Okay, so that is the claim. And now let me explain why this is true. First of all, this phenomenon, what's coming from the contact interaction, this is the cosmological analog of just the power series in ST and U. Right? You have contact operators, you just have something analytic, a power series in ST and U. Right? That power series in ST and U analog here is just the polynomial sitting upstairs. But what about this funny k1 plus k2 plus k3 downstairs? Okay? Well, that's not, there's no singularity there, because those are all positive numbers, right? But what is this? Well, we're doing something different between amplitudes and cosmology, right? Amplitudes, everything is in momentum space. Here, here position is in momentum space, but time is not, right? We're doing the measurement at a fixed time, fixed late time. So, in other words, back in the amplitude, there was something that was sitting there. There's also the delta function for energy conservation, right? We just strip it off. We don't talk about it, but there's a big singularity sitting there. Delta of if this was if this is an amplitude calculation, there would be a delta of E1 plus E2 plus E3, right? And here we don't get a delta of E1 plus E2 plus E3, but we get some power of 1 over E1 plus E2 plus E3. Okay? So why is that? Well, where did we get the delta of E1 plus E2 plus E3? We get the delta of E1 plus E2 plus E3 because we're integrating over time. We're integrating over all of time, d eta from minus infinity to infinity, e to the I, E1 eta, e to the I, E2 eta, e to the I, E3 eta. In other words, these e to the I etas are just the free propagation, just the e to the I omega t, which is always there in position space, which we're Fourier transforming in momentum space, and we turn into a delta function. Okay? So if you're used in courses to doing amplitude calculations or correlation function calculations in position space, or let's say just in position space for time, then all of these things, all of these propagators to the boundary would actually have factors like e to the I energy eta associated with them. Okay, that's just the e to the I omega t of propagation. So the delta function for normal amplitudes comes from the integral over all of time. We have a delta function because it's translational invariance. Okay, and that's what's imposing translational invariance. We have exactly the same situation in cosmology, but the integral, it's not translationally invariant. We're doing the measurement at a fixed time. So instead, we get integral minus infinity to 0 d eta e to the I e1 plus e2 plus e3 eta. And this is 1 over ignoring i's, e1 plus e2 plus e3. Okay? And now, the specific powers you have, maybe there's some powers of eta here, and we can change what the powers are. Okay? But the important point is that this piece is the analog of energy conservation for the cosmological correlators. Okay? So in fact, the analogy is really beautiful. The amplitude has a sharp singularity when e1 plus e2 plus e3 is 0. Okay? And then everything else is perfect polynomial. And that's the fingerprint of a contact interaction. The cosmological correlator has the analog of that, the softened version of that singularity. Okay? And again, it's a polynomial upstairs. Okay? All right, is that clear? All right. So now the important thing about this, therefore, is that just physically, if you take this triangle and you just ask, is there anything exciting happening? You know, is there some shape of the triangle where something dramatic happens to this non-Gaussian? The answer is no, right? Just a polynomial. You like move things around. It just depends smoothly somehow. Okay, but if you take the triangle, you make two sides long, one side skinny. You like fold it. Nothing is happening. It's completely smooth everywhere. In particular, strictly in this limit, which we'll talk about in a moment, in the limit where you take two sides long and one side short, so k short and two k longs, in this limit, the correlator is totally analytic. All right? All right. Now let's, so this is some hypothetical. How long do I have, Ian? 5 minutes. Ha ha ha. Ha ha. All right. All right. Let me just say something for 5-ish minutes, and then we'll pick it up. All right. Now this is some hypothetical contact interaction between the infotons. But let's talk about an interaction that's for sure there all the time. There's gravity there all the time, right? So gravity gives you a completely irreducible amount of non-Gaussianity. Perhaps Matthias will talk about this. And you can think of that in our language here as just being coming from a tree diagram with one graviton exchange. Okay, so it's the same. So I have there, I have a graviton, I have here, and I put one of these guys there. There's a graviton. Okay. Now, this was famously calculated by Juan Maldacena in 2001 or 2002. Okay. It's also almost completely determined by symmetries, as you might expect from our general discussion. But you might think, but when you do the calculation, it has exactly the same structure. It's 1 over k1 plus k2 plus k3, some power and some polynomial upstairs. Okay? It's also completely analytic. Okay? Now, that's maybe a little more surprising. You think there's this exciting massless graviton there. There's all sorts of stuff going on. But as we'll see in a little bit more detail when we understand what the signals for the massive particles are, in fact, what's going on here is that you would be trying to produce an on-shell graviton that on the one side, because you put the inflation to the background, would have to mix with and oscillate into a spin 0 particle, and it can't do it. Okay? So this process is not dynamical. It's not something, so let me say another feature. The reason why this function was so simple is that this thing was happening at one time. It was happening all at one time. Here you might think maybe you produced a graviton and it propagated there and nothing propagated there and it could be more exciting dependence, but it can't because a graviton can't turn into a scalar. So in fact, this effect is entirely the Newtonian potential. Okay, just the instantaneous attraction at one time between a pair of inflatons that popped out here and over here. Okay, so this is cool that both the thing which is forced on us by gravity, that's analytic, and anything we get from higher dimension operators is also analytic. Right? Okay. So now let's say you're an effective field theorist, right? And you say that I actually had a massive particle there, right? Let's go back to our d phi to the fourth example. Maybe I had d phi squared sigma. Oops, d phi squared times some sigma. And sigma had some mass, m squared sigma squared. Okay, some coupling. And so really, I'm integrating out sigma. Here's sigma. And that's generating my higher dimension operator. So I have kappa squared over m squared, and then I would have d phi squared, 1 over box plus m squared d phi squared. If I expand this out, this would be d phi to the fourth plus d phi squared box d phi squared plus ... Okay? So, well, again, if you're just thinking very technically, you would say, OK, that's a contact interaction. They're all contact interactions. So this is analytic, analytic. They're all analytic. Okay? So you say you integrate out a particle, and to all orders in the effective field theory expansion, the answer is analytic. Okay? OK, but this is actually not exactly correct. Okay? And there's nothing wrong. Effective field theory never lies. But effective field theory promises to give you the answer to all orders in h squared, Hubble squared, divided by the mass of the particle squared. Okay? And indeed, to all orders in h squared over m squared, the answer is analytic. However, there is an important correction, which is not analytic. Which is of order e to the minus m over h. Okay? I'll explain what this is intuitively in a moment. But I just want to contrast this with the story of amplitudes. So let's say you're sitting at low energies beneath the z mass. If you integrate out the z at tree level, you get an infinite tower of higher dimension operators. And if you measured all of them, you would know the amplitude at low energies exactly. Right? That is simply the statement that in this approximation, the low energy amplitude is dead analytic. Okay? It's perfectly analytic. And that's because the non-analyticity only happens when you produce the particle. And if you're sitting at low energies, you don't produce the particle. Now, this is the central difference between the cosmological collider and ordinary colliders. When we do flat space scattering experiments, we get to choose the initial state. And so if we don't like it, we ask for more money, and we build a higher energy machine, and we go to the energy where the particles are at. In cosmology, we have no choice about the initial state. We don't get to choose it. We don't know what it is, right? So that sounds bad. That's less freedom. On the other hand, especially in an inflating universe, it's a time-dependent background, and so whether we like it or not, it produces everything. The time-dependent background has particle production and can produce everything there is. Okay? So even though we don't have control, everything is produced at some level. Of course, the more massive a particle is compared to Hubble, the harder it is for the inflationary background to physically produce it, on-shell physically produce it, and that e to the minus m over h is exactly the famous Boltzmann suppression. If you want to think about de Sitter space as having a temperature h, it's just the Boltzmann suppression for producing the particle. Okay? So it means that if you have a particle that's 50 times heavier than Hubble, it's in principle there, but forget about it. However, if you have particles with a mass close to Hubble, then the inflation background is actually producing it on shell, right? And the piece of the correlator where it's being produced on shell is qualitatively different than all the other pieces that can come from higher dimension operators and other things, because the particle is produced on shell, exactly as for amplitudes. So let me just give me 3 minutes. I'll at least just tell you what, because the physics is so intuitive. Let me just draw the picture and say what the formula ends up being. Okay. So what happens is the following. So the inflationary background can pair produce a pair of particles, okay? A pair of massive particles. Okay, now this one is going to go and is going to maybe decay to a pair of infotons here. This one is going to go and it's really oscillating. See, one of them is on the background, so it's really oscillating into an infoton on the other side, maybe here. Okay. Okay? But what we have is exactly the physics of a standard physics of mixing phenomena. Okay? It's like K meson oscillations, B meson oscillations. You're pair producing two particles. And it's an interference effect. They're being measured. Okay? As you produce them, their wave function is evolving as e to the I mt. Right? It's roughly going as e to the I, their mass times t. Let's say the mass is bigger than Hubble parametrically. We can ignore the fact of the expanding universe and all of that. There's a wave function that goes like e to the I mt. There's an e to the I mt here. There's a different e to the I mt there. And so I get an interference that depends on the time difference between these two things. I get something that depends on e to the I m times t1 minus t2. Right? Now, what is e to the m? What is e to the t in inflation? E to the t is just the scale factor. E to the ht is just the scale factor, right? So e to the t is, and so what's going on here? These are going to correspond to things that happened at late times. Right? So those two infotons are being produced at late times. So they'll be at shorter scales, length scales, larger momentum scales. The first thing happened at earlier times, and it'll be larger length scales, smaller k. Okay? But e to the t, e to the t1h over e to the t2h is just the ratio. So in this limit, I have 3 k's. 2 of them are really big, and 1 of them is small. Right? The small one corresponds to large distances. That's this guy. Okay? This is late times. Short distances, big K, is these guys. The ratio of these two e to the t's is just the ratio of k short divided by k long. Okay?
So when you say short,
Right.
you mean units of Hubble?
Yeah, well, I'm doing a ratio, so it doesn't matter. Okay? Okay? So the ratio e to the t1h over e to the t2h is just this k short divided by k long. And the phase that I see, it's e to the plus or minus, and there'll even be some phase in principle, which is there. But what is e to the plus or minus im t1 minus t2? That is just that phase is just k short over k long to the power of im. Okay? No, k short over k long is a dimensionless number. Okay? So this phase is the ratio of this short length scales to these long sides of the triangle. So we should expect in this squeeze limit, in the limit where the triangle gets small, we're probing for the propagation of the particle that was pair produced. Okay? And the fingerprint that you have a particle that was pair produced is that the three-point correlator has to have these oscillations, right? It literally oscillates, right? So you make the triangle shorter and you make it more and more squeezed, and you see these oscillations. Okay? Those oscillations are the k-space analog. If we Fourier transform with respect to them, we'd get a pole. Okay? And that's the analog of sitting on a resonance when you do a particle physics experiment. Okay? So the fingerprint that you've produced massive particles is that you see these oscillations, completely non-analytic. You see these oscillations. All right, now let me say what the answer looks like in a little bit more detail. So the three-point function in the squeeze limit looks like, well, we've already seen there's a piece that's k short over k long to the plus im, and there's some phase here. And then there's a k short over k long to the minus im, to the minus I delta. It's very interesting. You can actually compute the phase. Okay, the phase is totally. But by the way, I didn't say any of this, but sorry, I should have said it. You see, in this limit, where the time separation between these guys becomes large, we also don't have to do any fancy calculations in inflation in order to compute what the coefficient of this oscillation is, because it's completely fixed by symmetries, exactly like it was for amplitudes. The reason is that when this time separation becomes very large, there is no difficult propagator from here to there. Okay? All I'm doing is producing this particle. So this effective propagator is with very small differences, the same as the propagator going all the way out to the boundary here and the propagator going all the way out to the boundary there. So what I get is the product of two three-point functions. Now, exactly the same logic as we use to determine the structure of the three-point functions on shell for scattering amplitudes also fully determines what they look like for these inflationary correlators. Okay, so the story is literally the same. In this limit, see, for the amplitude, when we go on resonance, all that matters is the product of the three-point functions. In cosmology, when we go to the squeeze limit, we are forcing a situation where there's such a big time difference between these guys that the time ordering between these events is irrelevant, and the propagators are essentially, again, the product of two three-particle correlators. So that's why we know the coefficients, and we can even compute the phase. We can calculate everything. Okay, this phase is a very interesting dependence on the mass of the particles, but I don't have time to explain it. But now, finally, there's a factor which there's a factor here which we haven't written down, which is also obviously there, which is that whatever effect I get from physically producing these particles has got to dilute with the expansion of the universe, right? Because I'm making the particles, and they're getting diluted by inflation. Okay, so that means that that there's something that has to go like k cubed. Okay. The actual probability has got to have an extra k cubed in it, right? Because the k cubed is 1 over a cubed. That's just the dilution with the expansion of the universe. That means in the probability, there's a k cubed. But in the amplitude, there's a k to the 3 halves, which is getting squared, right? This thing is an interference effect, right? Like a classic interference effect. So we actually get the k to the 3 halves here. Okay, so we get a k short over k long to the 3 halves. Okay? And finally, there's one last thing. I have this short side. Let me draw it like this. I have this short side and 2 long sides. So let's take a limit where the long sides are really, really long. And I have this short side. There's one final quantity that things can depend on. That angle. Okay? And, well, what do you think we're going to get? We'll get the Legendre polynomial of that spin as a function of the angle. Okay? Now, this structure is fully fixed by symmetries. This is the analog of Gegenbauer over S minus m squared. in a real particle physics collider. This is the analog of that for the cosmological collider. You cannot mess with this. You cannot fool it. It can't be faked with higher dimension operators. You see these oscillations, you've discovered a heavy particle up near 10 to the 14 GeV. Okay? So what are the things that make it difficult? Well, first there's the epsilon in front of all of these things, okay, for the three-point function. There is the very unfortunate e to the minus m over h. Okay? So we have to be lucky. We have to be lucky to have some particles not far from Hubble during inflation. And this is an extra little suppression. This k short over k long means that precisely in this squeeze limit, we're also, the effect is starting to get smaller. So what you would see, roughly speaking, as a cartoon, as you head towards the squeeze limit, you'd have some normal size non-Gaussianity. And then as you go to the squeeze limit, you start seeing oscillations like this that start getting damped. Okay? So there's the overall envelope, which is the k to the 3/2. And this is even if the particle mass is comparable to Hubble. Okay? Just from this effect of the dilution from the expansion of the universe, we're not likely to see 5 of these oscillations. We'll be lucky if we see one or two of them. Okay, but nonetheless, this is it. Okay, so this is the sense in which inflation can be used as an accelerator. This is the signal, and there are interesting scenarios where you might expect that this is something which could be visible at least at the level of the gravitational non-Gaussianity that Juan calculated a long time ago. That gravitational non-Gaussianity is the main target to hit for the next 20, 25, 30 years of measurement of large-scale structure and the CMB. And just to give you an example, you might imagine you have Harava-Witten extra dimension, something near 10 to the 14 GeV. They're not far from 10 to the 14 GeV. You can see KK modes. Okay? In any supersymmetric theory, there is at least 90 scalar fields, our superpartners, right? If it's supersymmetric anywhere beneath 10 to the 14 GeV, those particles are lying around. We could imagine looking for them. And finally, the most excitingly of all, I think, even though there's no good models for it, it's possible that what drives inflation is something much more stringy. That the string scale itself during inflation could be comparable to Hubble. You might think, doesn't that mean everything is screwed up and effective field theory is screwed up, higher dimension operators screw up everything? Absolutely not. All we have to assume is that there is this approximate de Sitter invariance and a very weak coupling, and everything else follows from symmetries. Everything we've seen so far, basically Gaussian scale invariant spectrum, follows from symmetries. So it could be the reason why all the attempts to do inflation in string theory look so ugly is because you're trying to fit a square peg into a round hole, and the standard picture of string theory is about calculating scattering amplitudes, and there's a more intrinsically cosmological phase of the theory, which is happier to drive inflation, but maybe, perhaps, the string scale during inflation could be closer to Hubble. Okay, we have no model for this right now. We have no idea how to formulate cosmology in any first principles way in the theory. But just as a qualitative thing, it would predict that you should see Reggie modes, right? Higher spin particles around Hubble. And again, this is how we can go about looking for them. Even though I don't know what the string theory is, it doesn't matter I don't know what it is, because I know what the signal is for it. Okay? I know what I have to look for to see this tower of higher and higher spin particles. And that's an example where you would expect it to be an order 1 correction to the gravitational non-Gaussianity. Okay? So we're a factor of 50 away from the gravitational non-Gaussianity today. But if we that's where people are trying to go. And this is a picture which would predict an order 1 modification to the standard gravitational non-Gaussianity with these sharp signals associated with it. So it's absolutely no substitute for ordinary particle colliders. This is still something quite remote. It has to do with inflation, things that couple to the inflaton. Whereas in ordinary particle colliders, we're learning about things that couple a lot to us, right? And so we need to do both things. But it's interesting that the experimental program in cosmology for the next 20 or 30 years could start giving us this window into incredibly high energy physics. And in any case, I think it's just kind of cool that in very subtle correlations of how the galaxies are distributed around the sky, you could see signals of ridiculously high energy 10 to the 14 GeV physics. And we know enough about the world and symmetries and everything else to be able to do it unambiguously ahead of time. Okay, that's it. And then in the next lecture, we'll switch topics, and I'll tell you a little about UV completion. Okay?
Then you're just pushing like k long to higher, and you just like
all that matters. You see, because it's scale invariant, dominantly, all that matters are the ratios. Okay.
So 2 questions.
Yeah.
First of all, K is momentum mode.
Yes.
Right? But then why late time has universe